Hi, I'm Manuel Beiran, and I'm presenting work in collaboration with Mehrdad Jazayeri and Srdjan Ostojic. The question of this project is, how are flexible timing tasks implemented in cortical areas? In particular, what type of neural dynamics can implement those flexible timing tasks? And secondly, what structure in the synaptic connectivity can give rise to those dynamics? We focused on two flexible timing tasks. First, the Q-set-go task, which is about flexibly producing either a short or a long time interval based on a cue presented at the beginning of the trial. The second task, measure-weight-go, requires first to estimate the time interval between two external stimuli, holding that interval in memory, and then reproducing it. In this work, we're assuming that the synaptic connectivity is given by a matrix that is low rank. This leads to neural trajectories that are low dimensional. What we did is first to train recurrent neural networks to solve a flexible timing task where the rank is constrained. Then we reverse engineered these networks to identify the mechanisms employed to perform the computation. Then we reproduce those same mechanisms in network models that are designed by hand. And finally, we implemented the timing tasks based on those network models. Let me show you some results of trained recurrent networks. For the Q-set-go task first, we found that the minimal rank to successfully train a network is 2. So neural trajectories will be 2-dimensional. When we look at the dynamics generated by these networks, we found that in all cases, they generate these slow trajectories that have this ring-like shape. Trajectories evolve at different speeds along these manifolds to solve the task. For the measure-weight-go task, which is a harder task that requires to estimate a time interval first, the minimal rank is 3. When we look at the dynamics generated by these networks, we found that they also generate a manifold that has now a spherical shape. And within this sphere, there are different dynamics, or at different locations, dynamics are different, so that the network solves the task. I move now to the mechanisms we identified that are necessary for solving the task and how to reproduce them in network models. We found that in all cases, the recurrent connectivity is generating slow manifolds, and the dynamics along these slow manifolds is also shaped by these recurrent connections. Then, external inputs can modulate the speed along these manifolds. Alternatively, in the absence of inputs, then the network can combine several manifolds in higher dimensions. For example, it can embed different ring-like structures on the surface of a sphere. We studied then how to generate these slow manifolds, and we found that in low-rank networks, it is important to have strong correlations between the different connectivity patterns in each of the rank 1 structures. These correlations are summarized in this matrix here, that, for example, in a rank 2 network would generate a ring slow manifold. Then we can add an external input whose amplitude would modulate the speed along this manifold whenever it's correlated with the connectivity patterns. Alternatively, we can also add one additional rank, and in that case, we would embed this ring-like structure on a sphere. So then we use these network models to implement the timing tasks. And I'll be happy to show you those results in the poster session. The conclusions of this work is that recurrent networks perform flexible timing tasks by generating these slow manifolds. And such slow manifolds can be generated by particular type of low-rank structure in the connectivity. I'll be happy to talk more about it during the poster sessions. Thank you.